Welcome back to che205. In this lecture, I'll be finishing the example we started last time, and that was example 4.2 of the textbook, calculating the integral of a function like this using trapezoidal rule as well as Simpson rule. So last time we talked about trapezoidal rule. This time we're going to see how we can calculate this using Simpson rule. All right. So let's dive into the spreadsheet. Okay, so for Simpson rule, we have to create pretty much the same table. We have x, we have f of x, and then now for the integral, which comes a bit tricky. For the first point, the integral is 0 because the area under the one point is 0, right? For Simpson rule, we go every other point. We cannot calculate the integral at every point. If I wanna calculate the area from 0 to 2, first of all, I have to have odd number of points, right? Let's say 2 points, 4 points, 5 points in total. You cannot split the interval into even number of points, including the endpoints, and use Simpson rule. For Simpson rule, you need to have an odd number of intervals. Let's see, from 0 to 0.5 is one interval, from 0.1 to 1 is another interval, for 1 to 1.5 is the third interval, and then from here to here is the fourth interval. So I actually take it back. For Simpson rule, you have to have even intervals or odd number of points. Okay, even intervals or odd number of points. In this case, we have 4 intervals, that's even, and then we have 5 points, right? 5 points for interval. Odd number of points, even number of intervals. Okay, and then in the calculation side, on this column, we only have the values at the odd points, right? The first point we have the integral, for the third point we have integral, and for the fifth point. We do not have the integral at 0.2 and 0.4. Okay, just keep that in mind. Okay, and there's a reason to that, because if you remember from Simpson rule, because of these coefficients, right? The first one and the last one is 1, and then the odd ones have coefficient 4, the even ones have coefficient 2. So because of that, we have to have odd number of points, right? These actually come in pair, like f1 and f2, we get a coefficient 4, 2, the next one is 4, 2, 4, 2, 4, 2, 4, 2, and then because they come in a pair, except the last one, right? So we're going to have odd number of points. Okay, I hope this is clear. Okay, so let's go back here, right here. Okay, then I go to the third point and use the equation. So the equation says the calculation from the previous interval, which is the blue cell here, and then plus 2 points B4, which is the green cell, right? So I'm sorry, which is this white cell on the x side. Yeah, that's well, yeah, you can think of the screen. That's okay. So this is going to be B28 plus 4 times the purple and plus the last one. So in this case, we have only 3 points. So the coefficient, this one actually doesn't come into the play. Okay, so we have the first point, the last point, and the middle point with the coefficient 4. If you have 2 more points, then I would get 2 and 4 again. Okay, so for only 3-point calculation, we have the first, the second, and the last. Okay, so that's what I have. B28, this cell, plus 4 times the next cell, and plus 1 times the current cell. Okay, so this is the area under this ribbon from 0 to 1. Then we go and add the area under the ribbon between 1 and 2. So we go to the next cell. I have the calculation on this cell, which is the area up to this point, and then plus the current ribbon. And the current ribbon is, again, the green cell, 4 times the purple cell, plus the brown cell, right? That's the sum of the functions, and then times the interval, which is the difference between the orange and then the orange and the green. That's delta x divided by 3, and that's according to the Simpson rule, right? H divided by 3. Okay, so at this point we get so that's the total area by this point, because I'm just accumulating as I calculate and go ahead. The good thing about this is as long as you calculate this, you can copy the equation and then paste it here. So then the equation actually gets forwarded and referenced to the right cells. Okay, so this is with h equal 0.5, and let's do this with h equal 0.2. So with h equal 0.2 we have more intervals. Let's look at the second interval right here. It's the previous interval or previous ribbon plus, now for this guy we're gonna have 1 times this end, 1 times this end, 4 times the middle one. Okay, and that's the sum of the legs, and then times h divided by 3, and the h is the difference between orange and the green cell on the x side. Okay, so we just copy this equation. You can just copy it and then paste it here. If you hold down the Command key in Mac or Control key in Windows, you can select all of them and then right-click on mouse, then paste. You get the equations on all of them with the right reference. You don't need to type equation on all these cells. So as long as you write one equation for the cell, you can copy-paste it on others, and immediately you get the result of the integral at the end. So compare this to this, and contrast this to the exact solution. Remember, we had the exact solution from the textbook. The exact solution is this much. You can calculate the error in percentage by subtracting the numerical value or the exact value from the numerical value, and then divide by the exact value times 100%. It gives you about 0.2%, and you see that with the same h value compared to the trapezoidal rule. Initially we got error of 2%. With the same h using Simpson rule, we get the error of 0.02, 100 times smaller. Same h, same delta x, same number of points. In fact, less calculation, because we have only 3 calculated values here as opposed to 5 calculated values for trapezoidal rule, and the error is about 100 times smaller. You cannot believe how much accurate the Simpson rule is. And if you do that for lower h, so let's look at this and calculate the percentage of the error, compare the two errors, right? Let's see, the error has gone down by a factor of, let's see, if I get the ratio of these two, that would be about 40, maybe 30. So let's do that. Let's divide. I'm going to divide this by this. So the error is about 30 times smaller. So I lowered the h by a factor of 2.5. Let's calculate this. So 2.5 raised to the 4th power, because Simpson rule is proportional. The error in the Simpson rule is proportional to delta x to the 4th power. And that's pretty much close, you see that? So that means the error has gone down by a factor of 2.5 raised to the 4th power, which is this number. So let's graph the error here. This is the error percentage as a function of h. The blue line is the trapezoidal rule. So for high h, we got high error. For low h, we get lower error. And the error goes down from here to here as you lower the h. Okay, so these are basically the points we calculated. So for trapezoidal rule at h equal 0.5, this is the error, is about 2%. Let's see here, that's about 2. And the error at h equal 0.2, the error is about 0.3%, which is about right here. So these 2 points correspond to these two. Actually, I put them in a table right here. For h equal 0.5 and 0.2, I have the error equal 2% and 0.3%, right? For Simpson rule, I put them in here, right? We calculated before. The error for 0.5 is 0.2%, and for 0.2 is 0.0008%. Okay, now let's draw the same error for Simpson rule. So at high h is this much, at low h is that much. I can click on that. You see that this I'm plotting this against this. All right. So the slope of this line is about 30 or 34. So the slope is exactly tell you. I'm sorry. The slope here is the order of approximation. So the slope here should be about 4, and the slope here is about 2. Let's make sure. So you want to calculate the slope. That's the height, which is about 2.5, right? This height is about 2.5 is the difference between this and that. And the base here is, I'm sorry, the height is the difference between these two, which is about, I would say maybe around 2. So the height is about 2, the base is about 0.25, so 2 divided by 0.25, that's about all right. So actually the difference is not 2, it's about yeah, so the difference is in the log scale, the difference is actually 2. So in the log scale, this height is about 1, and this base is about 0.5. So 1 divided by 0.5, the slope is going to be about 2, right? 1 divided by 0.5, the slope is about 2, which is exactly the second order or the order of approximation in trapezoidal rule. In Simpson rule, in the log scale, this height is about, I would say, you know, close to 2. So this is close. This is close to 2, and this is about 0.5, right? So in the log scale, this is about 0.5, right? Because from here to here is 0.1. From here to here, well, in the log scale, this is 1. This is 0.1. That's about 0.9. I think this range is about 0.5, and then 2 divided by 0.5, you get 4. So the slope here in the log scale is 4. Okay, so that tells us that Simpson rule is 4th order approximate, and Simpson rule is 2nd order approximate. And you see the slope is higher, that means the error goes down quicker than the trapezoidal rule. I hope this is not confusing how I calculate the slope, right? So in the log, we have to calculate the slope in the log scale. This is log, this is log. In the log scale, this is about 0.5, right? Because this is -1, this is 0 in the log scale. So this base is about 0.5 in both. In here, in the log scale, this is about 2. So 2 divided by 0.5, you get 4. That's the order of Simpson rule. And here the height is about 1 divided by 0.5, that's about 2. And that's the order of the trapezoidal rule. Okay, all right, so we did one example. We calculate the integral using trapezoidal rule, Simpson rule. We look at the order of approximation. We look at how the error goes down with respect to delta x. All right, okay, so in the next video, I'll be talking about the third way to calculate integral, which is Gauss quadrature. So stay tuned and thanks for watching.